Aluminium, once worth more than gold, now the metal that shapes our world. From the shiny soda can in your hand to the aeroplane soaring through the sky, aluminium is everywhere. But have you ever wondered, where does it really come from? Long before humans ever shaped it into cans, planes or skyscrapers, aluminium was born in the heart of stars. When giant stars exploded as supernovae, they forged elements like iron, silicon, and aluminium. Those cosmic fragments travelled through space, and billions of years ago, they became part of our young Earth. Today, aluminium makes up about 8% of the Earth's crust, making it the third most common element, right after oxygen and silicon. But here's the twist. Even though it's everywhere, aluminium never appears as pure metal in nature. Instead, it hides inside rocks like bauxite, and only through human ingenuity did we learn how to unlock it, turning stardust into one of the most useful metals on the planet. It all begins with a rock called bauxite. This reddish ore is the world's main source of aluminum. To use it, the ore is first mined from the ground and crushed into small pieces. Bauxite is found close to the Earth's surface, usually just a few meters below the soil, between 2 and 8 meters deep. It forms over millions of years, as tropical rains and weathering break down aluminium-rich rocks, leaving behind thick layers of ore on plateaus and gentle hills. The aluminum industry is built on two very different types of plants. First, the refinery, usually located close to the bauxite mines. Here, the red ore is transformed through the Bayer process into alumina, the fine white powder that contains pure aluminum oxide. Refineries are built near the mines because bauxite is bulky and costly to ship, while alumina is lighter and far more efficient to transport. Then comes the smelter, a completely different kind of plant. These facilities are not built near the bauxite mines, but in regions with massive sources of electricity. That is because turning alumina into aluminum metal with the Héroult process requires enormous amounts of power. So the journey of aluminum is always divided. Bauxite is refined into alumina near the mines, and alumina is shipped to distant smelters where cheap, clean energy transforms it into pure aluminium. In this video, we step back to observe one of the largest alumina refineries on Earth, standing along the coastline of Queensland, Australia. From the air, its scale becomes immediately clear. An industrial complex spreading across hundreds of hectares, designed to operate without pause, day and night, year after year. Each year, this single facility refines several million tons of alumina. The journey begins far to the north at the Weipa bauxite mine, one of the world's most important sources of bauxite. Here, the ore lies close to the surface, formed by long-term tropical weathering. After extraction, the bauxite travels by ship along the Queensland coastline, arriving here to begin a carefully controlled refining process. Through heat, chemistry and time, raw ore is transformed into fine white alumina. This is more than a refinery. It is a vast, continuous industrial system and a central pillar of the global aluminium supply chain. Before we look at how alumina is produced, it's worth understanding the infrastructure that supports the entire refinery. Closest to the centre, the administrative buildings serve as the brain of the operation, where planning, logistics and coordination keep everything aligned. Nearby, the main workshop functions as the refinery's backbone, maintaining and repairing critical equipment to ensure continuous operation. Just beyond, utilities supply the essentials: power, water and steam, the invisible systems that keep the refinery running day and night. Further out, bauxite stockpiles hold vast quantities of raw material, stored and managed before entering the production process. And at the far edge of the site, the wharf connects this refinery to global supply routes, linking inland resources to markets across the world. The process unfolds in 4 main steps. First, digestion. Bauxite is mixed with hot caustic soda under pressure to dissolve the alumina. Second, clarification. Impurities like red mud are removed. Third, precipitation. Aluminium hydroxide crystals slowly form and settle. And finally, calcination. The crystals are heated to produce pure alumina powder. In the digestion system, finely ground bauxite enters massive steel vessels with thick walls, engineered to withstand extreme pressure and high temperatures. Inside these sealed reactors, the slurry is heated to around 270 degrees Celsius. Under these conditions, hot caustic soda dissolves the alumina, forming a supersaturated sodium aluminate solution. Once digestion is complete, the liquid stream moves forward to the next system. With alumina now fully dissolved, the process shifts from chemical reaction to physical separation. In the clarification system, the process stream flows into large covered settling tanks with a circular shape and wide diameter. These tanks are shallow relative to their width, allowing flow to slow and gravity to act efficiently. Here, undissolved impurities settle to the bottom, while the remaining liquid becomes a clear, transparent solution containing dissolved alumina. This clarified liquor is then transferred onward for controlled crystallization. The alumina remains dissolved. The next step guides it back into a solid structure. In the precipitation system, the clarified solution enters open crystallization tanks with funnel-shaped bottoms. The liquid inside is visibly clear and gently agitated. At this stage, seed crystals are introduced, initiating early precipitation. The process then continues through tall, enclosed vessels arranged in long rows, where conditions are tightly controlled. Here, crystals grow gradually, forming aluminium hydroxide with a defined size and structure. The solid has formed. Now heat completes the transformation. In the calcination system, aluminum hydrate is transferred into high-temperature equipment. The material is heated to around 1,100 degrees Celsius. This heat removes chemically bound water, converting the hydrate into aluminum oxide, known as alumina. The result is a fine white powder ready for aluminum production. The alumina produced after calcination is kept in large warehouses with A-shaped roofs, with storage capacity reaching roughly 110,000 tonnes. From these sheds, the powder flows along the conveyors like a calm white river, sliding down the slope toward the wharf, where cranes load it onto ships for the long voyage across oceans. Alumina marks the boundary between mining and metallurgy. And to understand why the next step is necessary, we need to look back at how humans have historically mastered metal. First came copper, as far back as 9,000 years before Christ. It gave rise to the Bronze Age, when humans mixed copper with tin to forge stronger tools and weapons. Then came gold, around 4,000 years before Christ. Shiny, soft and easy to shape, it became the metal of kings and temples. Next was silver, around 3,000 years before Christ. Beautiful and rare, prized for jewellery and coins. Iron followed, around 1,200 years before Christ. Harder, stronger and far more common, iron reshaped civilizations, fueling empires and wars. And finally, aluminium. Even though it makes up 8% of the Earth's crust, it wasn't until the late 1800s that humans learned how to produce it in large amounts. The last great metal to join our story, born from stardust, unlocked by science, Ørsted tried first. He took aluminum chloride, combined it with potassium, and then tried to drive the potassium away, hoping pure aluminum would remain. The result? Only a few tiny specks, looking like silver dust. Then came Wöhler. He repeated the experiment with potassium and later tried sodium instead. Yes, he got more aluminum than Ørsted, but still just enough to keep in a tiny glass vial. Finally, de Ville stepped in. He had a new idea: use sodium, a cheaper and more available metal, as the sacrifice. This time it worked. He produced aluminum in amounts large enough to craft spoons and forks, luxury cutlery fit for Emperor Napoleon III of France. At that time, aluminum was so rare it was worth more than gold. And then came the real breakthrough. In 1886, two young scientists, Charles Martin Hall in America and Paul Héroult in France, working oceans apart, but at the very same time, unlocked the secret of aluminum. At the heart of aluminium production lies a controlled electrochemical process. First, alumina, aluminum oxide, is dissolved into a molten cryolite bath, creating the chemical conditions required for electrolysis to take place. Next, carbon anodes are lowered into the bath, forming the positive electrodes of the system. When a powerful electric current flows, electrolysis begins. Aluminum metal is released and slowly settles at the bottom of the cell. Periodically, the molten aluminum is tapped from the cell. Finally, it is cast into solid ingots, marking the completion of aluminum smelting inside the plant. At any modern aluminium smelter, operations are organised into several core functional zones. Each zone plays a specific role in keeping the electrolysis process stable, continuous, and controllable. long halls are the pot rooms. Inside, hundreds of electrolytic cells convert alumina into molten aluminium. Each pot operates continuously under tightly controlled conditions. Power comes from the electrical substation. Here, high-voltage electricity is converted into the massive direct current needed for electrolysis. Anode bake furnace is where carbon anodes are hardened before use in aluminium smelting. Inside the furnace, green anodes, made from petroleum coke and coal tar pitch, are carefully baked. Heat is applied slowly and evenly. Temperatures gradually rise to around 1,200 degrees Celsius, and the full baking cycle typically lasts close to 20 days. The rodding shop is the next stop for the anode on its way to the pot rooms. Here, an aluminium stem is inserted into the anode, and molten steel is poured around its base to secure the connection. This process ensures both mechanical strength and reliable electrical contact during operation. Operating around the clock, the rodding shop produces hundreds of finished anode assemblies each day, ready for installation in electrolysis cells. This is the gravity-fed Alumina system, where refined alumina enters the electrolysis process. Alumina is delivered from overhead hoppers and fed into each reduction cell by gravity. Once added, it dissolves into the molten electrolyte and becomes available for electrolysis. From this point on, the cycle begins. With alumina feeding in place, electrical current is delivered through the busbar system to the anodes. Inside each reduction cell, rodded carbon anodes conduct current into the molten bath. Each anode operates for about 20 days before being replaced. To see what happens next, we need to look inside the cell. Carbon blocks are manufactured on site and gradually consumed during operation, while remaining material is recycled and reused. The carbon blocks act as the positive electrode, or anode, while the carbon-lined cell becomes the negative electrode, or cathode. As electrical current passes through the molten electrolyte, an electrolytic reaction begins. The reaction separates alumina into molten aluminium and oxygen. Oxygen reacts with the carbon anode, forming carbon dioxide gas. Because of its higher density, molten aluminium settles at the bottom of the cell and is periodically tapped using a crucible. In a modern aluminium smelter like this one, production never stops. Each AP40 reduction cell produces approximately 4 tons of aluminium every 32 hours. Molten aluminium collects at the bottom of the cell and is periodically tapped, while the electrolysis process continues uninterrupted. At the casting shop, molten aluminium is siphoned into a holding furnace. Once the furnace is filled, it is tilted, allowing the metal to flow through channels and into moulds. Along the way, temperatures are measured at multiple points to ensure consistency throughout the casting process. Aluminium is typically cast into 3 main forms: small ingots weighing around 23 kilograms, sheet ingots weighing up to 35 tons, and sews, used primarily for remelting and further processing. Once cast and inspected, aluminium products are stacked, stored, and prepared for shipment. From the casting yard, ingots and slabs are transported to the port facility, where they are loaded onto ships bound for global markets. After the anodes are significantly worn, they are removed and sent for recycling to be reused in the process. We've seen the modern pot room, bright and precisely controlled. Now let's step back to an older era, when this same smelter had not yet received its comprehensive upgrade. The Soderberg technology, a process with no separate anode baking furnace, where the anode was formed and baked continuously right above each pot, and aluminium electrolysis depended on experienced human hands. An exception pot was a common issue with Soderberg technology, creating heavy fumes and high heat. The older Soderberg process required frequent replacement of electrical studs, and each change meant the pots were opened, allowing dust, heat and fumes to escape into the room. Molten aluminium in these vintage reduction pots follows a bottom tapping idea that struggles to part the metal from the shifting cryolite bath. The aging seal and the manually guided tapping pipe depend on a delicate angle and depth. When pressure or alignment drifts, the glowing stream can overflow the trough and slip beyond the channel meant to hold it. A small echo from a less forgiving era. Anode effect appears when alumina in the pot falls too low and the cryolite bath can no longer carry current smoothly. The voltage rises, gas builds beneath the crust, and the pot begins to hiss and glow with an unstable flame. Killing the effect is essential because if it lasts, the excess heat and emissions can damage the lining and waste energy. To correct it, operators feed fresh alumina and break the crust to release trapped gases, restoring the calm path for electrons at the bottom. Modern smelters often rely on automatic point feeders and real-time voltage control, while older pots demand closer human care and frequent manual intervention. The smelter moved beyond its old limits, and this brief look at the Soderberg era completes the journey. Thank you for watching. Share your thoughts in the comments. Tell us what you prefer, more science knowledge or more cinematic visuals. A story about aluminium or a closer study of the technology. And suggest new topics below.